Alright, this video explains the concepts of torque more in depth. Hopefully you've already seen the video that I showed you about the demonstration with torque. So all torque really is simply the ability of a force to cause an object to rotate around an axis. We've talked about forces in this class that are linear, forces that can cause objects to move in a straight line. We've also talked about forces that keep objects in a circle. In other words, we've talked about centripetal forces, but we haven't talked about forces that cause objects to move in a circular pattern or rotation, and that's a torque. Torque is an ability of any force to cause circular motion. In order for that to happen, the force has to act perpendicular to the object in order to cause rotation. And all that simply means is that, for instance, when you open a door, you push on the door itself toward the outside of the door as opposed to toward the hinges of the door. That's an obvious thing. If you wanted to open it, that's how you would have to push the door. A couple of terms that you need to know involving torque. The first one is fulcrum, and you've probably heard this term since your 8th grade science class. The fulcrum is the point around which the object will rotate. And in the example of this seesaw, which you should have a picture of it in your notes, it's right here in the middle. Okay, so this is the fulcrum where the object wants to rotate. These two objects are trying to rotate this seesaw in opposite directions. Another term that you need to know is the moment arm or the torque arm, and this is simply the distance from the fulcrum, which is circled, to the point where the force acts. And in the case of these two blue boxes sitting on the seesaw, these blue boxes are exerting a gravitational force on the seesaw, and it's that gravitational force that sort of desires, quote unquote, to rotate the seesaw. And so the fulcrum, or the moment arm rather, the torque arm, is the distance from the fulcrum to exactly where that force is acting. As far as the equation itself, this is the equation that you need to know for torque. And this is not a T, this is the Greek letter tau. Kind of looks like a backwards J a little bit. But tau is what we use to stand for torque, and torque is calculated by multiplying the force times R, which is the moment arm or the torque arm. It's the distance from the applied force to the axis of rotation. It's a distance, so it is measured in meters. Forces are still measured in newtons, and that brings us to the units for torque, which are newtons times meters. We simply get that from the equation itself. Force is measured in newtons, and R is measured in meters. That gives us newtons times meters. In other words, Newton meters. That's what we will say is the units for torque. And you can just write Nm on your paper, and that's fine. But torque equals force times distance. And it's an interesting thing when we look at this equation and think back on our demonstration that we've had. Because looking at this equation, it's really easy to see that there are two ways to increase the amount of torque that you're applying on something. And that is, you can increase the force, or you can increase the distance from the axis of rotation. Increasing the distance is the thing that most often is the easiest thing to do. Very few of us can actually very quickly get stronger and be able to apply more force, so the easiest thing is to simply get something longer to push with so that we can be farther away from the axis of rotation. It's actually an interesting concept to consider when we look at this equation, because this equation is not too unlike the impulse equation that we looked at a while ago, where in many collisions what we said was that the J, the impulse, cannot change. It takes a given impulse to bring about a given change in momentum, and what that means is that the force and the time can kind of compensate for each other to make the same impulse. And that's the concept behind an airbag. With an airbag, what you do is you increase the amount of time that's allowed for the collision to occur, and when you increase the time, that means that the force can actually decrease in order to keep J the same. That's the way that an airbag can save your life, is because it can actually decrease the force that's applied to your face. And it's the same concept with torque. With torque, it takes a given torque to turn something, whether it be a door or a screw or a nut, whatever it is, it takes a certain amount of torque to do that. And that torque is determined by the force applied and the R, the distance away from the fulcrum that we apply the force. So this is the same thing. To get the same torque, all we really need to do is increase the R, and what that does is it can drastically increase, or decrease rather, the amount of force that needs to be applied. Let me show you an example of that. Here I am standing at the door. Hopefully you can hear me. You all know how to open the door. We simply push the door open. That's not that big of a deal. But it's interesting to consider, and maybe you've done this before, perhaps you've held the door open for someone before, and if you do that, sometimes you have to push on the inside of the door to allow them to walk through, right? And you might have noticed that that's a little bit harder to do. And the reason why it's harder is because you're pushing on the inside of the door. You'll notice that this is a torque. This door is rotating when it opens, and the axis of rotation is here down the side of the door where the hinges are. And if I push as far away from the hinges as possible, it's really easy to open the door. In fact, I can use one finger and open the door. Not a problem. Because I increase R, I've increased my distance from the fulcrum, which means that the force that I have to apply to get the same torque can go down. But if I push over here on this side of the door, nobody does that. And the reason why they don't is because it's really hard. And if you push with one finger over here, I guarantee you cannot open the door. And it's hard to do. You can do it with one hand, but you have to put your whole weight into it. Okay, so this is a really good example of how increasing the distance can decrease the amount of force you have to apply. And as a matter of fact, in the demonstration that we did with the wrenches, that concept is seen in that demonstration as well. All right, in the real world, there are lots and lots of things that we come in contact with on a daily basis that take advantage of torque. One is the transmission of a car or a bike. How a transmission works is you have multiple gear wheels that are different sizes, and those different sizes mean they all have different radius. Okay, and the one with the largest radius means that you have to apply the least force to cause it to move, to cause it to rotate. Whereas the one with the smallest radius takes the most force to get the same torque out of it to move the car. And you might notice in your bicycle, if you start out in 5th gear, it's possible to get the bike going, but you practically have to stand on the pedals. And the reason is because you're using a very small gear with a very small radius. And since R is decreased so much, you have to increase the amount of force to get the same torque. So that is seen in a transmission. It's seen in wrenches, which we saw in the demonstration, screwdrivers. With a screwdriver, you've never seen a screwdriver that's simply a piece of metal. There's always a handle on the screwdriver, and that's for 2 reasons, one of which so that you can get a grip on it. Number 2, it increases R. It increases the distance from the axis of rotation. Crowbar, the same thing. It's a lever and you apply a fulcrum to it. The longer the crowbar, the easier it is to pry whatever you're trying to pry. And then doors, like I showed you just now, and a door stopper. If you put a stopper under a door, you want to put it as far away from the hinge as possible. If you put it near the inside of the door, it probably won't work. The door will most likely shut on you. All right, there are a few kinds of example problems that we're going to do. Here's one of them, and I'll do this on the notes for you in just a second. Let's take the example of the door. If you push on a door with 30 newtons of force at a distance of 55 centimeters away from the door hinge, how much torque are you applying? Let's do that problem real quick. All right, so this is what I would call a single torque problem. They're the most simple. It uses this formula, and we're simply going to use the guess method again. We do all the time. We are given the force that we use. We know that we're using 30 newtons of force to open the door. It tells us that we apply the force 55 centimeters away from the door hinge, so that means that our R is 55 centimeters, and if you see centimeters, we need to convert it to meters, and we do that by moving the decimal 2 places to the left, so that gives me 0.55 meters. They want to know how much torque. That's our unknown. The equation we use is obviously the torque equation that we've just learned, and now all I need to do is substitute and solve. 30 times an R of 0.55, and if you calculate that, 30 times 0.55 gives me a torque of 16.5, and the units are Newton meters. That's the answer. These are very simple problems. Single torque problems are very, very simple. Let's look at another single torque problem. Look at the second one on your notes. The second single torque problem says, what is the radius of a bicycle gear that applies 75 Newton meters of torque to the chain when your feet apply 536 newtons of force to the pedals. So again, we're given, they tell us that the torque is 75 Newton meters on the bicycle wheel or the chain. Your feet are applying 536 newtons of force, and the problem wants to know what's the radius of the bicycle wheel, what's the distance from where the force is applied to the axis of rotation. And on a bicycle wheel, there's the chain, that's where the force is applied on the outside of the wheel, and the distance from there to the axis of rotation is the radius of the wheel. Once again, torque equals force times the distance times the radius. 75 is our torque, our force is 536, and we're looking for R. Divide by 536 on both sides, and you should get a radius of 0.14 meters or 14 centimeters converted. Probably means a little bit more to us. There's another single torque problem. Alright, last one. Look at your notes in the last problem. The last problem in the notes say that it requires 30 Newton meters of torque to loosen a lug nut. So I know that the torque is going to be 30 Newton meters. They want to know how much force we have to apply to the handle of a 22 centimeter long wrench to loosen it. So if my wrench is 22 centimeters long, that means that R, the distance from where I'm applying the force to the axis of rotation, is 22 centimeters. And again, that needs to be converted, and it's 0.22 meters. Same equation, torque equals force times distance. The torque is 30, the force is what we want to know, and the distance is 0.22. And if I divide by 0.22 on both sides, I think you find that the force is 136 newtons approximately. So those are pretty simple. Those are single torque problems.